So in this video, we want to talk about the basic calculus that we're going to use in the AP Physics class. And I want to run through some of these kinematic graphs again, just to refresh your memory on them. So when we have position, velocity, and acceleration, we have three sets of graphs we can talk about: constant position, constant velocity, constant acceleration. So remember, if I have an object that's just sitting still, it's not moving anywhere or going anywhere, so that position graph is going to be a flat horizontal line. Because the position is not changing, remember that the velocity is equal to the change in position over the change in time. Well, if the position isn't changing, then the velocity is going to be zero. The object isn't moving. And remember again also that the acceleration is equal to the change in velocity over the change in time. And if the velocity over here isn't changing, then the acceleration has to be zero also. Now, if I have an object that's moving at a constant velocity, maybe you're in your car, you're driving 70 miles an hour down the interstate, that means that your velocity is staying at 70 miles an hour. That means every hour your position is going to be another 70 miles further away, so you're going to increase in this linear diagonal line. And again, remember that if the acceleration is the change in velocity per time, because the velocity is constant here, there is no change in velocity or time, so that's going to end up being zero. Then when we look at the final graph, maybe this is you are standing on top of the bleachers at a football game and you're dropping water balloons on passerbys. So when the water balloon is falling, it is falling according to the acceleration of gravity, which is negative 9.8 meters per second squared, or let's just say negative 10 meters per second squared. So it's falling at a constant acceleration, that 10 meters per second squared downward. So every second, the speed of the water balloon is going to get 10 meters per second faster. So the first second it'll be 10 meters per second, the second second will be moving at 20 meters per second, third second will be moving at 30 meters per second, which means that the position, because it's getting faster every second, it's going to cover more and more and more distance every second. And so you get this really beautiful exponential line that comes off of that. So now there's a couple things that we can look at with this. Well, let's say slope to begin with. If I look at these two diagonal lines, I can define slope to be m equals y over x. So what is on the y-axis of our position graph? Isn't that really our position? And what is on the x-axis of our position graph? That's going to be time. Well, what is position divided by time? Yeah, you got it. We set it up here. It is equal to the velocity. So really the slope is telling us the graph that is to the right. So when we look at the velocity time graph, we can say the slope of this is going to be y over x again also. What's on the y-axis of the velocity graph? It's the velocity. What's on the x-axis of that graph? Well, all of the x-axes on here are time. What is velocity divided by time? Yep, you guessed it. It is the acceleration, or the graph to the right. So when we talk about the slope, we're moving right on the graphs. Then we can look at that and say, well, hey, isn't that interesting that y divided by x means something? What can we look at? Like, maybe this is a really easy one. What if we look at the acceleration one and say, I wonder if y times x means anything? And if this is a rectangle, then won't y times x really be the area that's under that curve or under that line? So what's on the y-axis here? It's the acceleration. What's on the x-axis here? It's the time. Well, what is acceleration divided by time? Yeah, it's the velocity. So when we talk area, the area goes the other way. So the area under the curve is going to be y times x, and it will move left on the graph, just the same as the slope moves to the right on the graph. So again, we could look at this guy and say the same thing. We could say, hey, the area here is going to be y times x, which is going to be the velocity times the time. And isn't velocity times time the x position, which is going to be the position on that side of the graph? So depending on where you pick that time value, it will give you a different area that tells you exactly what the position is at that point in time. Now, when we talk about slope and area under the curve, this is where the calculus comes in and becomes very exciting. The slope is nothing more than the derivative, and the area is nothing more than an integral. So whenever you start getting into upper level calculus, try and keep in mind that that's really, at its most basic, the derivative is a slope, or sometimes we would call this a gradient, and the area is the integral area, slope, derivative. So how do we find the derivative then? We're going to take, in number one, multiply the coefficient by the exponent. So I'm going to take this 3 value, I'm going to multiply it down here into the front, so the coefficient of that is going to be 1, so 3 times 1. Step 2 then, I'm going to take that exponent and drop the exponent by 1. So I'm going to subtract 1 from the exponent, and that will give me 3x squared. And then one last one that's not really a step, it's kind of on its own, is that the derivative of any constant is 0. So if I took the derivative of 3 with respect to x, then I'm going to get 0. And in essence, I'm taking this guy up here, a little bit of notation. I would be saying the derivative of x cubed with respect to x. So this tells me down here what I'm taking the derivative with respect to. So if I practice some of these down here, let's kind of look at where this would go. So first step, multiply the coefficient times the front. So I would take 4 times 2 and get 8. Drop the power by 1, 3. Plus 3 times 3 will give me 9. Drop the power by 1, 2. And then what's the derivative of a coefficient? It's 0. So plus 0 equals 0. And that's going to be the derivative of that. Next one, I'm going to take 2, the coefficient, times the negative 4.9, so I get negative 9.8t, drop the power by 1, so that would be to the 1, I don't need to write it, plus, this is implied to be 1, so 1 times 45 will be 45, drop the power by 1, well, what is t to the 0? Anything to the 0 power is 1, so I don't need to write it, and then the derivative of a constant is 0, so I can put that to be equal to 0. Then, if I take this last one, I can say, well, dx with respect to time is going to be what? Well, what is position with respect to time? The change in position over the change in time is really going to be my velocity. So I can take 2 times a half and get a t, drop the power by 1 and get 1, plus 1 times vi, drop the power by 1 and get t to the 0, which is 0, and then take the final one, which does not have a time value, so it's a constant, and set that equal to 0 because the derivative of a constant is 0. And notice that we have this kinematic equation that when you take the derivative of it, you get another kinematic equation, VF equals VI plus AT. Now let's talk about integrals. So if I'm taking an integral, sometimes the integral is called the antiderivative because it's really just the opposite, or one way to think of it is the opposite of the derivative. Kind of like division is the opposite of multiplication, addition is the opposite of subtraction, or vice versa in all those cases. So the first thing that I'm going to do, step 1, is I'm going to raise the exponent by a power of 1. So whenever I look at this, the notation is I'm going to say I want to take the integral of 2x squared with respect to x. Because if I'm integrating with another variable, that will totally change what I'm doing. So I'm going to take the exponent of the x, and I'm going to raise it 1 power, so 2 plus 1 will be 3. And then I'm going to get rid of that little, I'm not sure why that's there. Then I'm going to divide the coefficient by the new exponent. So I'm going to take 2 and divide it by the new exponent 3. And one of the ways I can double check myself on this is if I take the derivative of this, I'm going to take the exponent 3 times the coefficient, which will get rid of the 3 here and leave me with the 2 in the front. And then I'm going to drop the power by 1, which would give me the x squared. And so I can tell that I did that correctly. Now, there's one more step to it. If this is a definite integral, then I will put a from value at the bottom of my integral sign and a to value at the top. So maybe I might be going from 0 seconds to 10 seconds. Or maybe I'm going from, since I'm dealing with position, I'm going from position 0 to 100 meters from now. I'm running down the football field or on a track, 100-meter dash. When I do that, then I would take this final value and I would do the from value minus, the to value minus the from value. So if I did the 0 to 100, then I would take and do 2/3 times 100 cubed minus 2/3 times 0 cubed. That's what we would call a definite integral because we're running from something specific to something else that's specific. If we have an indefinite integral, then we don't really know where the beginning or the end of this is, so we have to say there's got to be some starting point here that's going to be a constant. And because we're looking at a position here, then our constant has always got to be the initial value. So in this case, it will be the initial position value. Now let's do some examples. If I look down here, I have the 3x squared plus 4x plus 2 equals 0. I want to integrate this with respect to x. If I do something on one side, I should do it on the other also. Integrate with respect to x. So I'm going to take the x squared, raise the power by 1 to the third, divide by that new power. So 3 divided by 3 becomes 1, and I can just leave that blank. I'm going to take and raise the power by 1. 1 plus 1 is 2. Divide by the 2, and that'll give me 2. And then I'm going to raise this one. Now remember, this is really 2x to the 0, because anything to the 0 is 1. So I'm going to raise that by 1, x to the 1, divide by the 1, and get the 2. Now, if this is an indefinite integral, because I didn't give a from and a to, then I'm also going to add a constant on the end, which in this case will be my initial position. On this side, we can look at it and say, well, what is the derivative that gives me 0? And isn't the derivative that gives me 0 some constant? And so on this side, I'm going to have a constant too. Now, 9 out of 10 times, what we'll do is we'll take that constant and we'll lump it into this constant over here. And so I would just keep the 0 on this side. So let's do the same thing over here. Again, this, when I integrate it, will become a constant, but that constant will fall into this integral over here. So if I integrate this, since my variable is time, let's integrate it with respect to time. Remember that this is like saying x to the 0, so I'm going to raise that power by 1, divide by the new power, 12 divided by 1. I'm going to take this guy, and instead of x here, we're going to look at this and say, it's a rough morning. So let's look at this guy now. So what we're going to do is we're going to integrate this with respect to time, because t is my variable. I could integrate the 0 here, but remember, we'll do the same thing we did up here where we lump that constant into the constant of this integral. So imagine this to be 12t to the 0, because t to the 0 will be 1. So I'm going to raise that power to 1, divide the 12 by the new power, 1, and I end up with 12t. Over here, I'm going to take this t, and I'm going to raise the power by 1 to square it. Then I'm going to take and divide the negative 9.8 by 2 and get a negative 4.9. And then I'm going to have plus some initial time value, and then that's going to equal 0. And what's usually our initial time value going to be? Usually it's 0. We'll just say, hey, we start at 0. So let's do the same thing down here. Let's integrate this and this with respect to time. So if I integrate the right side first, I'm going to take the t here, raise the power by 2, and I'm going to get 1/2 a. Are you starting to see where this is going? And then I'm going to say, hey, this is really like saying t to the 0, so I can raise that to the power of 1 and get vi. Yep. And notice that I'm starting to get an equation that looks something like this over here. And if I take velocity times time, same thing over here, I'm going to take v times t. This final, isn't that really going to be the position or the distance or displacement that we covered? Now, don't forget, these were indefinite integrals, so I have to add an integration constant. And in this case, it's going to be whatever my initial position was. So this would be where I finally end up, my x final, and this would be my initial position. And so that gives you sort of a summary of the derivatives and integrals. Now, there are a couple common ones that you'll need as we run through the course. You don't have to memorize these right now. As we practice them, you'll get them. Some of them will be like whenever we get into sines and cosines, then we would say that the derivative of the sine of theta with respect to theta is going to be the cosine of theta. We would say the derivative of the cosine of theta with respect to theta is going to be the negative sine theta. So there's sort of a repetitive or looping set of derivatives. Then we would also say we want to talk about, well, what happens if my x value is in the denominator? So I'd say d, the derivative of 1 over x with respect to x. This has got to be kind of goofy, because if I take my power of 1 and I subtract it, then I get some strange stuff going on here, and that integral is going to be the natural log of x. And then there's one last one that we would look at for the most part of what we're studying now, we would say, well, what about if we talk another log value where I have the derivative of the log of negative ax, e to the negative ax, and in that case, we would take the derivative of the exponent, so negative a, and then it's just times the log itself again. Any other derivative or integral, you're going to look on the AP sheet or Google it, and then you can just skip this part. We're not going to look in the appendix on our book, so because you can find all those derivatives online. So hopefully that gives you a summary of sort of the position, velocity, accelerations, how we get what slope and area are. Remember, slope is the derivative, area is the integral, and then it's a quick and easy way to do derivatives, do integrals, and some common ones that you might need.